Hello, everyone. I'm Dmitry Petrov. I think we are ready to get started. Please let me know if you don't hear me, don't see my screen, my presentation. Today we are going to talk about data versioning in generative AI, about efficiency in machine learning, and the primary focus would be LLM use cases and texts, but it can be applied at different modalities such as computer vision and others. The focus would be on data preparation, data curation, and how to efficiently do this, how to use like a right data structures. We will touch a little bit about the cost of LLMs and how to measure cost and optimize. So let's get started. A little bit about myself. I created open source tool DVC, data version control, like a few years ago. And now we are working on more and more data related tool. And today we are working in a new set of functionality for generative AI use cases. So I will show you some development that we have that will be like released later this year. Before I was a data scientist at Microsoft for numbers of years. I work for Bing. It's a search engine. And the funny part is today when I see modern LLM application, there's so many analogies and so many techniques that we used as a search engine can be applied for LLMs. So we will be talking a little bit about this as well. As an example, we will be using LLMs, as I said. The data set is user bot transcripts, which was provided by KIT institution. It's a chatbot like a log, right? And we will be analyzing how good the bot behaved when interacting with the users. For models, we'll be using cloudy models, like a different actually models, Opus and Haiku. And the data set is a 79 dialogues from this data set, which is a perfect size for demo. But in reality, you might expect like a bigger scale. We'll talk about the scale as well. So this is how dialogue looks like, right? So bot asks some cheers the user, right? And then discussion starts. So the goal for the bot is to provide a good suggestions of a product for user, which is suggestion for the plan. For the network, for the phones, right? And dialogue is successful if a user get good information, or if user get a good answer that's dialogue that this plan does not exist. So short agenda. First, let's talk about the challenges in LLMs. Then search engine, complex system, and analogy with the LLMs and search engines. And the good portion of the talk would be examples, right? We will be coding in Jupyter notebooks. I'll show you like how it actually works. So if you are hands-on, and you can enjoy the second part of the talk with the examples. And I will also, of course, explain like how it works in enterprise settings, in companies, like how companies can apply and do apply these techniques to improve their efficiency and collaboration in the team. All right, challenges. So many companies today are working with LLMs. I mean, almost all the companies in the world are working with LLMs, trying to optimize their expenses, open new scenarios. But there is a tons of different types of challenges, right? LLMs, they're kind of like not deterministic. And sometimes the return result like a different result, and it depends on like sometimes just randomly you ask LLM the same equation for the same prompt with the same data 3 times, and you get like 3 different answers, right? Or sometimes you change your prompt just a little bit, and the result like changes completely, right? Like in this example, I just changed wording a little bit, and the result is like get from success to failure. So, and that's like reality people are living today. Output format is a big challenge, because in many cases you want from LLM like a multiple dimension of the answers. Like say if I need to know if the dialogue was successful or not. So same is success or failure, and explain the reason why it failed or why it was successful, right? And sometimes you are getting like a give me JSON. Sometimes you are getting like a good JSON. Sometimes you are getting like list of JSON. Sometimes you are getting JSON, but format is a little bit different. Sometimes JSON with some text, and you need to deal with this kind of formatting challenges. Variability of answers, right? I told in the beginning, I said like sometimes you run like a multiple query, the same query multiple times, you get like several different answers. So this is example, like give me the reason why dialogue was a failure, right? Give me like a top reasons. Okay, out of 80 dialogues, 79 dialogues, you see the first response have some intersection with the third. So this like a two types of responses. They do match for each single dialogue. This response, like this color, presented only in the first one, and the red one presented on the second one, right? So, like it's kind of like a variability of these responses makes this a little bit complicated. And at the same time, another challenge is like it's a cost. When you ask these questions dozens, hundreds, thousands of times, you need to pay for these like API calls, and sometimes it costs you like substantial amount of money. So which means like a number of like your experiments is kind of limited. And even if you run infrastructure on prem and run these heavy models on prem, LLM models on prem, you still need to have like a GPU and such. So it's not actually free, right? And for some customers, we have done some research on like how to evaluate the spending on prem models versus like API calls. So we shouldn't be surprised that this doesn't go for free. All right. From data point of view, the way how to deal and how to be more efficient is to use like a right data structure for responses, requests, version them, and efficiently deal with these data structures, right? In such data structure, I mean, like usually people prefer to work with on validation stage, prefer to work with like vectors, data frames, SQL tables, and such. The question is like how to get faster to this right data structure so you can get this result. You can get the validation like really efficient, really fast. So the funny part, about the search engine. Today we deal with these LLMs, and these LLM applications are pretty complex systems, right? When you build like LLM, you usually deal with a few agents, right? One agent like ask question, the second validates response, the third compose the third the next question, or the next like analysis of the response. It might call some external APIs. It can give the result to the third or fourth agent, and so far and so on. It's a really complicated system. And even if one agent is not predictable, how to deal with all the complexity, right? It becomes like a whole black box when output and input like are not clearly connected to each other. And the funny part is search engine works like a lot. There are a lot of similarity with the search engine. When you query like some question, right, to the engine, it also triggers multiple ML models. Number of models depends on your query, right? Sometimes it's like a couple of models, sometimes it's like dozens. So these models are organized in some cascade, right? The same with LLMs. You have like a multiple prompts, multiple requests to the LLM. They are connected to each other, right? There is a complicated cascade. LLMs might be like even more complicated because the cost of creating this model, like it's pretty small, right? You can generate like many different prompts. And at the end of the day, the good portion of the search engine is like how you validate this result. And a lot of work is done on the offline modeling, offline evaluation. And on search engine, when I work for a search engine, we spend majority of our time for offline validation. to like build the model, how much it affected our target metrics for this, what is the coverage for like a user base for this particular like segments, and etc., etc. So a lot of validation is done before it gets to not even to production, but to try a small slice of traffic to the production, right? To make sure it affects metrics, actual metrics efficiently. And today I see more and more discussions in LLM community about the validation, how to validate, how to deal with these probabilities, how to deal with this instability, and etc. And the way to go is to, it's a validation, offline validation. It's a key part to this problem, and it kind of introduce bunch of metrics to your black box. So your on your input, you still kind of like sometimes maybe not easy to get the output, but at least you have a lot of metrics to understand what is inside. And in order to do this, you need like efficient tools, efficient representation of your data for the validation. So that would be our demo about how to validate data. So, and there is we will go through 4 subtopics in the demo. So first of all, okay, we crafted a prompt, get data, issued a query to the LLMs, and get some result. But how to efficiently store this result and efficiently work with the result? In many cases, people prefer to specific data structure, right? Like a data frame, DB tables like SQL, or maybe just vectors. And we need to get to this like as soon as possible, right? Your data ML engineers should not waste time on this serialization, deserialization, etc. It needs to be efficient, of course, right? We are talking about like parallel distribution processing, and you probably don't want to rewrite your code if you decided to run and distribute it. Cost efficient needs to be part of this process, of course, because LLMs are not cheap today. And saving result and versioning result, that's a good portion of validation. That's what helps you to keep track of your work and collaborate with the teams and be more efficient as a team. All right, let's go to the examples, to the demo. One second. So, okay. This is Jupyter Notebook we will be using today. So let me import some libraries first. This is our prompt. And you see, like in application, usually prompt become like a pretty complex. So if you ask like some naive question, like, "Hey, how complex is it? Was the result, was the dialogue good or not? Did bot provide value for user or not?" Right? If you ask such kind of like naive question, you will get like a naive answer that might not help you. But you need to be like very specific, of course, like what you need. The roles like user, bot, how they defined in the dialogue. What is the success, right? If bot able to gather information and offer a plan, blah, blah, blah. What is not success, right? And how to provide the output. I need JSON file. It should be like success or failure. It needs to provide the reason, and etc. Right? So that's our prompt, and then the models. We will be using Anthropic. 2 different models. First, we will start with the heavy model, and then we go to the cheap one, and we'll be comparing them against each other. So we go through this step. Prompt is imported, I guess. Okay, let's go through the steps again. Data would be in a Google storage, text files, 1 dialog, 1 file. We get all the data, and let's look at the files. So file name, size, some dialogues longer than others. And then we need to get like query the system, and this is like how request to Anthropic looks like, right? You provide the service which we created, specify the model, which will be using Opus model, the prompt from the above, and the data from the file, right? But the challenge is the service generate like quite a complicated structures as an input. So that's the structure, right? So if you import message, the result it returns, you'll see this structure with ID, with a content, which is list of some other structure, with model name, roles, blah, 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 usage, and etc. We kind of like need all of those. At the same time, like, do we want to like code all this information? Probably not. But the good thing is it's based on Pydantic in this case. So we are lucky we can get this kind of, it's designed to be like serializable, this class. And that's advantage we will take. So we have in the framework the conversion from the Pydantic object to what we call feature set or feature. So we will get the structure which can be like easily serializable to like data frame or data table. So, and now we take all our files, right? We have like 89 of those. In this example, I will limit only by 5 random files, and then apply this like function, lambda function. It's not lambda, but function, to generate the response. And the response is, yeah, our class, which is based on the original one. And we will be returning this class in the data frame. So, not fast. It says like 5 seconds per row. So one request takes like a 5 seconds for us. So that's another topic about the efficiency, right? And then we got the result. So the ID, the content, status, success, failure, tokens, input tokens, output tokens, so we can evaluate how expensive it was. That's basically the idea, right? You can look at the requests, the actual reason, right, behind this. And as you see, this was pretty slow, right? 5 iterations per second, 5 seconds per one file, per one dialogue. And we can definitely do better, right? With parallel execution. The service actually cannot give you like parallel more than 4 threads. This is how they decided to kind of limit the rate. And we will be using core 4 threads. We wrap this result a little bit to extend text, status, and explanation to different columns. So it's a little bit different function, a bit different class. And yeah, let's run it. First, it runs all the 79 files, right? You see like 20 rows. Oh, it's Heiko. Yeah, I need to replace it to Opus actually. Okay, let's wait until it's done, and then we can run the Opus model, the good one. Where is it? Yeah. Okay, Opus. Running this again. We run this with the Opus model with a big model in 4 threads. The speed is faster than it was, right? Now we are processing like 1 row per second. And that's crucial to kind of work efficiently and parallelize this kind of tasks. That's especially important when you run in a bigger scale, right, with thousands and millions of requests. And even more important when you work on the distributed, when you want to use your model on-prem model, right? When you run your like a Mistral model or such. In this case, you might need like a parallel compute, not a distributed compute, not only parallel, right? But some additional machinery might be needed, like here. We run pretty much the same framework, the same code, but it's run on a cluster of like a six GPU workers, right? And distributed across 6 devices. So, all right. In case of like external models, like several threads is enough. It's almost done. And once it's done, we can look at the result. We just converted this to pandas directly and visualize as a pandas. Yeah, here you go. So files, e-tags, then you see the explanation here, right? In one column, status, success, success, failure, failure, again, success. And now you can start evaluating the stuff, right? And through the such API, such a data frame or SQL, it's much easier to run this kind of analytics. When you deal with a small scale, like 80 signals, it might be not a big deal, but still, it's better to be prepared to like any scale you might need and apply like a good techniques. So here we see the success rate, right? Just like filtering out by success and then divided by a number of columns. We can look at the actual data, failure, success with the explanation. So we will not go deeper here, but if you get to the list, you will see what its actual explanation was, right? The boss was able to gather all the necessary information, offer, mobile plan, blah, 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 right? So you can go like deeper to the understanding. But the interesting part is we paid money for the service, right? And let's calculate like how much we pay. And we do have the signals in our model, as you remember. So the price of the Opus model was $15 per millions of input tokens, 75 for output tokens. So let's do this 15, 75. And then we see that we spent $1.40 just to get this rating for the 79 quakes, right? So that's a lot of money, right? So, you can go and check like $1 store how much you missed it's with a $1. So okay, now we can analyze maybe prompt and start like first of all, like let's remember this model, right? It will be like our Opus model. And now we can iterate through this process and try like different techniques, like how much success rate we will get if you change prompt a little bit, how it's different comparing to the current one, right? Or maybe we can change something else. We can optimize the spendings, right? And let's replace our model, our Opus model. So what is it? Yeah, here it is. To a cheaper one, Haiku, and do the same thing. So the good news is it should be faster. So you see like 3-4 rows per second instead of 1 row per second. And I hope we pay less for this. And then we can see like result, like if we are paying less, can we get the same like success rate comparable? Or is it a good success rate or bad success rate, right? That's like the questions you might ask from the application point of view, from your use case point of view. So, okay, we got result, the same thing, right? Success, failure, explanation, all the stuff. We can calculate success rate. It was almost 60%. Now it's 80. Higher. Is it good or not? We don't know, right? We need, first of all, like a ground truth to decide on this. And second, it heavily depends on your applications, what you optimize for. But we get some metrics, we get something that's a good step. So the reasons and pricing. Okay, pricing. Let's get to the price of Haiku model. It's at 25 cents for input and 1.25 for output. So 0.25. Okay, 25 and 125. We run it again. You see from the data table, right? We see this input tokens and output tokens. We basically read this data from the table we got. 2 cents. That's quite a difference, right? Comparing to almost $1.50. So good. Now let's compare those two models. So we got like a one variable on Opus and one on Haiku. We calculated the success rate, right? It was increased with the cheaper model, which might be good, might be not. Let's first of all merge this two and look at the result. And you can compare. You can look at the. Okay, this table is a little bit too big. Let's look at the other table. Let's look only on the file name and ratings. So that's like a bigger, smaller slice, bit better slice. So one model says it's success. The next model says it's success. This is success. Haiku says it's failure, right? There is a difference. And explanation are also different, right? So let's go a little bit deeper to this. Why don't we just build a confusion matrix on this? So we are getting data from Opus, renaming just to make it nice, right? Like Opus signal would mean like a status. And Haiku signal in the Haiku dataset will mean status of the Haiku. And we join these two, merge these two on the name of the file. So, and then convert to pandas and create a confusion matrix here. Okay. Failure, 12 cases out of 79. Success, 44. And mismatches, 20 here and 3 there. So the Haiku model, the cheapest model, is a little bit more optimistic about our rate, and that's might be like a good thing. Good thing, might be not. Again, dependent on the application. But the point is, like with a good framework, you can get faster to the data structure you prefer to work with. Data frame, SQL. This can be like translated to SQL, and under the hood actually works on SQL. And it gives you you become more powerful on analyzing the result and evaluating of your applications. All right, and the last part, but not least, it's versioning. And the result that we built, the table of Opus and table with the Haiku dataset, they can be saved, right? And next time, I mean, maybe like tomorrow, you can read the data. And technically, it's saved in a local database right now, but it can be like a global one, a centralized one. You can get this result as is without like running the query again and again, right? And do your analytics, do your analytical queries evaluation later. In case of like teamwork, it's better, of course, to have this like a registry of your data set that people can share and collaborate on, right? But in this case, so instead of like sending like Parquet files and such, you can have like a centralized database with reference to data sets, right? So this kind of like a data set registry with a data set versions, like who created, when created the data set, and reproducibility when you can trace back to the source code, requirements files and such, so you'll get the better understanding and reproducible results. In case of usual application, like local applications, you can commit this result to Git, right, and use Git for reproducibility and such. So that's depends on your teams and preferences. So that was the demo. 1 second. As a conclusion, we can say that a lot of effort happening right now on LLM validations and evaluations. I see a lot of interest in this space. Right now, especially when applications become more and more complex with multiple agents working together, having a good data structure can mainstream your validation process a lot, and data version helping you to keep track of the validations and better collaborate with the team members. So thank you for your attention. Happy to answer the questions. We have maybe 10-ish minutes for the questions. Folks, any questions? Please welcome. Happy to discuss deeper. Oh, good one. Yeah, is the notebook is available to try? Yeah, happy to share. I will provide my socials. So happy to share the notebook. However, the library, the DVCX library that we use was not open sourced yet. It will be open sourced a little bit later. So as a concept, yes, you can look at this and provide feedback. So I'd love to hear your feedback, but I don't think it will work. Question from Ilona. Is DVC for data versioning is the MLOps workflow only MLOps workflow only, or the whole activities? Can you tell a little bit more about it? Absolutely. So DVC and the tool I showed you, right, DVCX, it's kind of like extension of the DVC. They are designed for like dealing with unstructured data. And our core use case, of course, machine learning and AI, and we heavily optimize for these use cases. But application can vary. For example, we do have users and even paid customers who do, for example, like simulations. Because they still deal with data, they need version of the data, unstructured data sets, right? They need to extract insight, they need to like keep track, keep versioning of the stuff. So yeah, it's kind of like focused more on ML and AI, but it can be used like a little bit outside of those domains. Is that your own internal fork of DVCX? It's a DVCX. It's not released yet, but it's our kind of like the only the only fork we have so far. So it will be released like later in a year, so you can play, and like would be great to hear your feedback. Another question from Ilona. Until now, I only use DVC for data task. Good to know there is more. Yes. Yeah, DVC that you see right now, right? The DVC framework contains like multiple parts, like data versioning, experiment tracking, and model registry. And all together with the Git, it can be used for reproducibility. The DVCX, it works upstream from DVC. It helps you to create a data set that will be used for DVC for MLOps downstream. But yes, data part is definitely the stronger part of DVC. Thank you for the question. All right, let me share my socials. So that's 1 sec. Please, you can reach me out on Twitter, on LinkedIn, email. Please don't hesitate to reach me out. So I appreciate when people ring me up after a talk, and happy to chat about your use cases, your challenges, share our ideas. Yeah, please reach me out. Thank you for your attention. Have a great rest of the day. And notebook, Kelat asked about notebook that I forgot. Could you please ping me on one of the socials, any of the socials or email? I will bring the, I will share the notebook with you, or anyone like who reach me out. Thank you, folks. Have a good day.